Hello and welcome to this course about finite volume method in C++. My name is Mohammad Saris and I'm a postdoctoral researcher at De Montfort University in Leicester, United Kingdom. And in this particular course, we'll be trying to implement the finite volume method in C++ using object-oriented techniques similar to those that appear in SU2 and in OpenFOAM, but not as sophisticated as that because that would take some time and it's not suitable for a beginner level. There will be some classes required for this particular project, and we will implement a class for the grid or the mesh and a class for the fields, which is like u velocity, v velocity, pressure, etc., and a class for the finite matrices, AE, AW, source terms, coefficient matrix basically, a class for the boundary conditions, and we just move this away, a class for the solution setup such as time, step size and all that, and a class for the output, which is where we write the solution data to a visualizable structure or a file. Okay, so we'll be using a co-located grid, which is more practical when you go to advanced levels rather than a staggered grid. Here on the co-located grid, just I will give some basic explanation and then we'll get into the grid later a bit more. We have some control volumes with round nodes, and we have some spacings. For example, here this purple color node is the center of the control volume and it's denoted by the letter P, which is the central node. And we have some faces of the control volume, namely the east face, the north face, the west face and the south face. And one cell ahead we got the east, one cell up we got the north, one cell to the left hand side we got the west, and one cell below we got the south. And we also have to calculate some spacings, basically the spacing between the central P and the face, and also the central P and E and W and S. So it's denoted by, for this particular purpose, dx1, dx2, dy1 and dy2. And this is required to calculate some interpolation factors, and so that we can calculate the variable values at the face rather than at the central position. Okay, so basically the grid class that we are going to implement is it will be made from a structured grid, and in the beginning it will also be a grid which has the same spacings in x and y and the same number of nodes. So on these nodes we have some distances called x and y, and with respect to that we calculate the central values or the cell center xc and yc, and from those xy, xc and yc we calculate the interpolation factors, namely the fx and the fy, and also with the distances that we measure we can calculate the cell volumes and cell face areas. And as we go ahead this will become more clear and clear. In the fields class we will implement fields that can hold the UVP, which is the U velocity, the V velocity, the pressure, the temperature, etc. And also once we implement the grid class, we'll make sure that the fields class can access the information about the grid without actually calling the grid class. So that will kind of save some time and make things easier for us. Now this fields class can be made quite complex, such as you can implement these fields to have a separate subclass for vector fields and for scalar fields, etc., for boundary fields. But at this level we keep it simple. So if desired, operators can be defined to make one field, for example, u multiplied by v, or v multiplied by p, or divide or added together. Now, the finite matrix class, probably one of the most important class in this particular project. Um, Distinctly, the finite volume operations results in some coefficient matrices, such as, for example, diffusion, convection, advection, or the pressure source, pressure gradient source. These leads to some coefficients like AE, AW, AN, which is the coefficient towards the east side, west side, north side, south side, and some source terms. So uh, it's kind of different from what we usually see in finite difference methods, where we directly go and find out the values after one iteration for u, v, p, and etc. Here we actually have to find out each of these finite volume method, for example diffusion or something, what's the coefficient matrix going to be for that particular operation. And that's why we need a class where we can hold all this information together, um, and it will make things easier in the long run. So we can define a class and also define again operators to overload, so that we can add, subtract, etc. the finite matrix resulting from various operations in the finite volume method. Again, another important class that we need to implement is the boundary conditions. So a separate class that holds the boundary conditions such as Newman boundary, Dirichlet boundary, no slip, extrapolated boundaries, etc. can be implemented easily. But we have to note that there are two types of boundary conditions when we go for finite volume method. One is a boundary condition that modifies the values of fields such as velocity, pressure, etc. For example, let's say you have an inlet and you want to specify that the u velocity or the x velocity is a specific value at that boundary, then it will belong to this case number one. But there's another kind of boundary condition where it modifies the finite matrix, such as the central coefficient or the source terms. So we have to know and be able to distinctly differentiate between these two types of boundary conditions. Okay, so we'll come to talk about that a bit more as we go along. This is just an introduction. In the solution class, we actually don't need to implement this class. We could just easily write what the time step size, what the under relaxation factors, etc. is. But it would be nice to have all these settings that we will use throughout the project in one class, rather than finding out where or what each of these is. So we'll implement a solution class as well. And finally, we implement an output class or a file writing class, which will write the UVP in a tecplot structured data format so that we can visualize what is happening. So to summarize, we implementing finite volume method for the lid driven cavity case using these classes on a co-located grid and visualizing the solution to make sure that everything is okay. So I hope you enjoy this particular course, and see you in the next video.